Dear student, the most important concept in this chapter is dimensions of a physical quantity. What do you mean by dimension? Previously, in the beginning of the chapter, I have introduced about fundamental and derived physical quantities. I have already mentioned how to represent the derived physical quantities in terms of fundamental. So the nature of a physical quantity is described by its dimension. All the physical quantities can be expressed in terms of the 7 base or fundamental quantities, that is mass, length, time, electric current, thermodynamic temperature, intensity of light, and amount of substance raised to some power. The dimension of a physical quantity are the powers to which the fundamental or base quantities are raised to represent that quantity. So this is the definition of the dimension. I repeat, the dimension of a physical quantity are the powers to which the fundamental or base quantities are raised to represent that quantity. So simply, dimension is nothing but the power which is present for a fundamental physical quantity. Note: using the square bracket around a quantity means that we are dealing with the dimension of the quantity. So whenever you have a square bracket, it represents the dimension. Example: the dimension of volume of an object R. Now how can we represent volume? Volume is nothing but length into breadth into height. All the three, length, breadth and height, will represent the length alone. But why they have different name? Because to differentiate with respect to one another, we have given a different name. But actually, length, breadth and height, all three represent the length alone. So volume is nothing but length cube, so which is represented as L cube. Now here if you see, what is the dimension of volume in length? Yes, what is the power here? 3. So 3 is the dimension. Remember, what about the remaining quantities? There is no mass, there is no time. So there comes a question in the examination saying that what are the dimensions of volume in mass and time? Now generally volume is represented only in terms of length. There is no mass, there is no time. So you have to write 0. Suppose if the question is asked like this, what are the dimensions of volume in length? So what is the dimension here? 3. So we have to write the answer as 3 in length. The dimension of a force R. Now force is represented as ml t power minus 2 because ma, F equal to m into a. Mass means capital M and acceleration means Lt power minus 2 meter per second square. So Lt power minus 2. Now if you see, what are the dimensions of force? We have to say like this. If anybody asks a question, what are the dimensions of force? The answer is 1 in mass, 1 in length and minus 2 in time. The dimensions of energy are, energy is nothing but work done. Work done is nothing but force into displacement. So force is nothing but ml t power minus 2. Length is nothing but L. So ml square t power minus 2. So the dimensions of energy are 1 in mass, 2 in length and minus 2. But so dimension is nothing but the power to which the fundamental or base quantity are raised to represent that quantity. So simply dimension means the power. Dimensional quantity. Dimensional quantity is a physical quantity which has dimensions. So a physical quantity which has a dimensions are called dimensional quantity. Example: speed, acceleration, momentum, torque, etc. Dimensionless quantity. There are certain physical quantities which don't have dimension. Remember, a quantity which has no unit will not have dimension. Dimensionless quantities is a physical quantity which has no dimension. For example, relative density. Now, what do you mean by relative density? Density of a substance to the density of water. So, it is a ratio of two similar physical quantities. So, no unit, no dimension. Refractive index, strain, etc. So, these are the quantities which do not have dimension. I repeat, no unit means no dimension. Dimensional constant. Dimensional constant is a constant which has dimensions. For example, universal gravitational constant, Planck's constant, Hubble constant, Stephan constant, Wien constant, Boltzmann constant, universal gas constant, Faraday constant, etc. So all these are proportionality constants which comes in derivations. So if the constant is having dimension, it is called as dimensional constant. Dimensionless constant. So there are certain constants which do not have a dimension. So dimensionless constant is a constant which has no dimension. Example 5. 5 is a number which is a constant. Pi, which is 22 by 7 or 3.14, E, 0.38, etc. Dimensional formulae and dimensional equations. The expression which shows how and which of the base quantities represent the dimension of a physical quantity is called dimensional formula of the given physical quantity. I repeat, the expression. So dimension formula means expression, base quantity. So the base quantity should represent the dimension of the physical quantity is called the dimensional formula. Example, the dimensional formula for volume is, initially in the previous slide we have seen that the dimension of volume is L cube, but that is not the dimension formula. How we have to represent MLT. So, but volume is having only dimension with respect to length. Then what about mass and time? We have to give 0 because anything to the power 0 is 1. So it will not affect. Second one, the dimension formula of speed or velocity is, generally speed or velocity is nothing but meter per second. Meter means length, second means time. So LT power minus 1 is the dimensional formula for speed or velocity. But we have to write it as m power 0 L t power minus 1. The dimensional formula of acceleration is m0 L t to the power minus 2. An equation obtained by equating the physical quantity with its dimensional formula is called the dimensional equation of the physical quantity. That means if you equate this dimensional formula with respect to the physical quantity, that is called dimensional equation. Simple. Volume is equal to m0 L3 t to the power 0 in square brackets. So this is called a dimensional equation. Like this. Velocity or speed is nothing but m0 lt to the power minus 1. Acceleration is equal to m0 lt to the power minus 2. Quantities having the same dimension formula. Some physical quantities will have same dimension formula. Example, impulse and momentum. I hope you have learned about impulse and momentum in class 9. What is impulse? When a sudden force is going to exert for a short interval of time, it is called as impulse. In Newton's second law, when you are deriving the formula F equal to ma, you may come across an expression F is equal to delta P by delta T, or delta P is equal to F into delta T. Here this delta P is nothing but either momentum or change in momentum, which is also called as impulse. In the same way, work, energy, torque, moment of force will have same dimensional formula. Generally, work done always will store in the form of energy. So in order to have energy, we have to perform some work. In the same way, angular momentum, Planck's constant, rotational impulse, all these will have same dimensional formula. Stress, pressure, modulus of elasticity, energy density, all will have same dimensional formula. In the same way, force constant, surface tension, surface energy. You will learn all these content in your class 11 in further chapters. So whenever the concept is going to come, I will introduce the terms one by one. So you have to wait till that moment. In the same way, angular velocity, frequency, velocity gradient will also have same dimensional formula. Gravitational potential, latent heat will also have the same formula. Dimensional formula for a physical quantity often used in physics are given at the end. That means in the end of the chapter, I'll discuss about the dimensional formula. If you really want to learn the dimensional formula before, you can see your textbook.